And we have begun recording. So I'm just going to introduce some of the basics of non-standard analysis that will be used in part 3 of the talk. And then in part 2 of the talk, I'm just going to torture you with definitions from the paper so that I can state the main theorem. And it is unfortunate that there are many, many definitions needed before I could state the main theorem, but we can save that for next week. So, as some of you may know, if you've heard of non-standard analysis, you can discuss it or talk about it using set theory, but I don't know any of that set theory, so I'm just doing a concrete construction using ultrafilters, which is hopefully going to be understandable to everyone in this meeting. So pick any non-principal ultrafilter. Doesn't have to be idempotent or anything, just whatever ultrafilter you like. And after you pick one, I'm just going to fix it for the rest of this talk. I'm going to refer to this underlying ultrafilter every now and then. And now, once you have an ultrafilter, you can create an equivalence relation on the sequences of natural numbers, or if you would like, sequences of real numbers, depending on whether you want to construct the non-standard naturals, you would start here. If you want to construct the non-standard reals, then you would start here. And the equivalence relation is that two sequences, the sequence of AIs and the sequence of BIs, are going to be equivalent if and only if the indices for which they agree, the set of indices for which they agree, is contained in your ultrafilter P. And the fact that this is transitive, it just follows from the fact that ultrafilters are closed under intersection. And the fact that it's reflexive, I think, is pretty clear. So it's an equivalence relation. Now, the non-standard natural numbers and the non-standard real numbers, we construct them the same way. We start with n to the n, and then we quotient by the equivalence relation to get the non-standard naturals. And if you want the non-standard reals, we start with r to the n, all real sequences, and then we quotient by this equivalence relation again. And it's always denoted by putting this star to the left instead of the right. Because I guess if you put it to the right, that already means non-zero elements of a field and is used in other places. As far as I know, that's the only reason they would put it to the left. And we can view, I guess this isn't really a ring, because even the natural numbers are not a ring, but the non-standard naturals and non-standard reals, they're closed under component-wise addition and component-wise multiplication. So they certainly resemble the original spaces from which they came from. And the non-standard reals are a field. And it's at this point that we actually use the fact that we had an ultrafilter and not just a filter, because this equivalence relation is going to be an equivalence relation for any filter. The fact that we're using an ultra filter is what allows us to see that the non-standards are a field. And I'm just going to give a proof. I was planning on giving lots of proofs today just because they're kind of short and easy, and hopefully it'll just make us more comfortable with working with the non-standard reals, since the proof that I'll hopefully show you in part 3 is basically just a bunch of calculations with non-standard reals, which is relatively easy if you're comfortable working with them.
So are all the proofs that, for example, addition of non-standard reals and multiplication of non-standard reals, like the proof that that's well defined, I guess, is just uses the basic properties of a ultrafilter? Is that?
So So this is I see. So your question would be, if we were to change this representative
Yeah. Mhm.
and this representative, then would it still fall in the same equivalence class? Well, so, I guess, yeah, the fact that addition and multiplication is well defined does also rely on the fact that we're using an ultrafilter and not just a filter. So, I guess at this point I should probably switch to the seamless. Now, we know that the n's such that an is a prime n is going to be in P, and the n such that Bn equals B prime n is in P. So the n such that An plus Bn is equal to or no, I guess this is just the filter property. Right. The places at which they agree is going to contain the places at which the sums agree.
Mm-hmm.
And this
And maybe some more
intersection.
stuff too. Yeah. Okay.
Yeah.
Cool.
Same thing for multiplication.
Yeah.
And then we know that if we take two non-zero numbers, then since they're not zero, the set of indices for which the components are not zero has to be in the ultrafilter. Otherwise, they would be equivalent to zero. So then, once again, the intersection of these two sets contains the set of indices for which the product, or I guess this time it's exactly equal to the set of indices for which the product is not zero. And therefore, that's also going to be in the ultrafilter.
Okay.
And I guess this just shows that it's a integral domain, but you can also just see the inverse is right. If I was to multiply these two numbers, I would just get the sequence that's 1 everywhere. The multiplication is defined for P almost every coordinate,
Mm-hmm.
since P almost every coordinate is not zero.
Yeah.
So then it shows that your integral domain is also a field. And basically what I did here is, right, if you have a function, then the way you apply it to your non-standard real number is you just apply it to all of the components. We're going to end up doing that for any function.
And so just to be sure, if you took a principal ultrafilter, then the non-standard reals are just the standard reals, right?
Yes, that's a good point. I did not think about that, but if you pick a principal ultrafilter, then you're basically saying I only care about one coordinate.
Yeah.
And if you restrict to one coordinate, then you're just back to standard reals or standard naturals. Mm-hmm. So yeah, that's interesting.
Sohail, do you know an example of a almost zero number if you change ultrafilter by filter?
What do you mean almost zero number?
So I don't know if this is true, but my impression is that the issue is that you could have like many elements that look like zero, but they are not really zero. So the ultrafilter is helping you have only one zero. Or something along those lines, right? That's where the ultrafilter part is coming in.
Oh, you're right. I still only used the filter property here and not the ultrafilter property.
No, so Hill, in the step where you said the set of n where Rn is not 0 is in P, that's the ultrafilter property. Because all that being not 0 means is that the set of n where Rn is equal to 0 is not in P.
Yes.
And so now you're taking the complement and saying it is in P, which is the ultrafilter property.
Oh, okay. Thank you.
And I think that's what I think more or less what Rigo is pointing out, that if you don't have the ultrafilter property, then you can have something that's not 0, but the set of indices where it's non-zero is small.
Right. So if you take, I guess
Or not
the
big.
standard example is if F is the cofinite filter, then what?
Okay, yeah.
Is not 0 and this is not 0. But then AB is 0.
Mhm.
So are we any more questions, or are we?
We're very happy.
Excellent. That's what I like to hear. So now one of the nice properties that's preserved is that non-standard numbers are still ordered. So if we take a non-standard number, it doesn't matter if you're saying non-standard natural or non-standard real, you can define that number to be bigger than or equal to 0 if the set of indices for which it is bigger than or equal to 0 is in your ultrafilter. Sorry about that extra bracket. And then, of course, we just define it to be strictly bigger than 0 if it is bigger than or equal to 0 and it is not equal to 0. And then this lets us define ordering where if we have two non-standard numbers, one of them is bigger than the other if the difference is bigger than or equal to 0. And I guess here, I think I'm using the ultrafilter property again, just to say that, right, we have n such that an is bigger than 0, n such that an is equal to 0, and here. Right, this is going to be all possible indices. So one of these has to be in the ultrafilter. And that's going to determine whether the number is positive, negative, or 0. So again, this is something that wouldn't work for the Frechet filter, but works for any ultrafilter.
So is this ordering, I forget the word, it's like anti-reflexive or whatever, where if you have, you know, it being like if x is greater than or equal to y and y is greater than or equal to x, then x is equal to y. Do you have that?
Yes. This is I guess, I assume that all orders are anti-reflexive, but this one is, it does satisfy that property because
I'm pretty sure it's actually not anti-reflexive, but I don't know what the name is, so but I don't think it's anti-reflexive.
So your question is basically if x is bigger than or equal to 0 and x is smaller than or equal to 0, then x is 0.
Yeah. Yeah.
So this would mean that if I, and you know what, since I already wrote A, let me. So if A is bigger than or equal to 0, then that would mean that the union of these two sets is in the ultrafilter. If A is smaller than or equal to 0, then the union of these two sets is in the ultrafilter. So their intersection is going to be this set, and that will be in the ultrafilter. So therefore,
okay.
A is 0.
Okay.
So Yes. Thank you for the question. Yeah, this is what I was hoping to do today, is just to ask these basic questions and
Oh,
then
good.
just realize that because we all understand ultrafilters, everything works out. And I don't know about you guys, but I did not understand any of the set theory when I first tried to read this.
Yeah.
But any other questions on the ordering or anything that has happened so far? Okay. And as you may expect, the ordinary numbers or the standard numbers embed inside of the non-standard numbers, whether you do natural numbers or real numbers. And of course, even if you were to do rational numbers or some other ring, you would get the same embedding. I'm only focusing on non-standard naturals and reals because that's the only thing we're going to need for the proof I'm going to present in part 3. But you might be interested in thinking about how this applies to other rings or fields. I'll leave that to you. So if you just take an element in the base set and just map it to the tuple where that element occurs for every single component, then this is going to be an isomorphism of the original set into the non-standard set. And we can certainly see that it's injective because if this element is not 0, then the set of indices for which the tuple is not 0 is everything. So that's in the ultrafilter. It's certainly additive homomorphism, multiplicative homomorphism. So it's also a, maybe I shouldn't have said isomorphism, but isomorphism onto its image. And these elements are just the standard numbers because they come from the standard numbers. There's nothing non-standard about them. Now, in the natural numbers, we see that every non-standard number is going to be bigger than every single integer. So any non-standard number, any non-standard natural number is going to be infinite in this sense. And we can verify this. So if we take a non-standard number here, and since I'm working in the naturals, I can assume I'll leave this part as an exercise, that because every natural number is bigger than or equal to 1, if you start taking these tuples, then the resulting non-standard number is going to be at least 1. So this part should be not too difficult. And if we also have that this non-standard number is smaller than or equal to some integer, then we can do the following. So we take the difference, it's non-negative. So the set of indices for which these ANs are at least 0 is in P. So the n's such that K minus Vn is bigger than or equal to 0 is in P, where this is the components of your non-standard number. So now here. So if this happens, then Vn is just going to be some number in between 1 and k. So we just partition this set into k sets based on the value of Vn. And then if the union of the k sets is in your ultrafilter, then one of the k sets is in the ultrafilter. So then that tells you that your non-standard number must have actually, V was a standard number the whole time. I think I might have taken the long way around this, but hopefully it made sense in the end. Any questions or concerns? So yeah, this is a little weird that any non-standard number is going to be infinite if you're in the naturals. But in the real numbers, that is not the case. So, of course, you can still get non-standard real numbers that are bigger than every standard real number. So we can easily construct an example of that. Right, this is even an example of a non-standard natural number that's bigger than every natural number. And every natural number is a real number. Every non-standard natural number is a non-standard real number. So this is an example for both cases. All right, we could see that the set of indices for which this is larger than any given number R is cofinite. So it's certainly in our ultrafilter. But now, when we're working in real numbers, we have the opposite. We have infinitesimal numbers. So epsilon, a non-standard real number epsilon, is going to be infinitesimal if it is bigger than 0, but smaller than every standard number R. And hopefully you could guess before I write it down how I'm about to construct an example. It's pretty similar to what I've already written. So, oops. All right, we can again see this is certainly positive. Every single coordinate is bigger than 0. But for any given real number, the set of indices smaller than that, or any positive real number, the set of indices smaller than that positive real number is cofinite. So this number is infinitesimal. And these are certainly gonna, infinitesimal numbers will be useful in the proof for part 3. And then the third definition is a non-standard real number is bounded if it is bounded between two different real numbers. And we can certainly see that this is necessary. This rules out the infinite case. Now, some of the, I guess some more properties about these is, if we have a bounded non-standard real number, then it has a standard part, which is the supremum of the real numbers that are smaller than it. And again, just to give you a very basic example, right? If you pick your favorite real number, then you can construct a non-standard real number by just adding 1 over n to the n plus first component. And it's certainly non-standard at this point. It is not the same as R. We can see that this is larger than or equal to every real number smaller than R, but it is strictly smaller than any real number bigger than R. So this supremum is just going to give you R. And in fact, we see that well, maybe I should just get rid of this to make it the same epsilon that I had on the previous page, and that would just be slightly nicer. Was someone about to ask a question?
Oh yeah. So I guess you haven't gotten there. I was pre-unmuting my mic, but so you say V1 is infinitesimal and V2 is bounded, then V1, V2 is infinitesimal. So I suppose you could have V1 infinitesimal and V2 unbounded, so that V1, V2 is bounded and not infinitesimal. Like that's a thing that happens, right?
Certainly.
Okay.
In fact, right? If you multiply these two numbers, you get 1.
Oh, yes.
An unbounded number times an infinitesimal number is equal to 1. And of course, you could adjust
But not always, right?
Yeah, not always. This is just one
Okay.
example.
Yeah.
Example.
Okay, cool.
Right. If you made these squares,
It would be
then
0.
the product would still be infinitesimal. If you made these squares, then the product would be unbounded. Right? If you multiply
Oh, yeah, you're right. Yeah. Okay, cool.
Yeah, multiply this by 2, and then the product is going to be 2.
Right.
So the product of an unbounded number with an infinitesimal number could really be anything. I mean, well, yeah, it could just be anything.
Cool. Thank you.
So can I ask, so I'm a little confused. If instead of taking R plus epsilon here, you took R minus epsilon, then we'd still have the same standard part, right?
Correct.
So infinitesimals can also be negative. Is that right?
Yes.
Okay. So I think I think
well,
you just talked about positive ones so far, but I think you need them to be negative.
That's true. I should have.
Makes sense to me.
I should have permitted them to be negative as well.
Okay.
Sorry.
No, that's fine. I just was trying to make sure what was going on here, that I wasn't missing something.
Yeah, I just guess I didn't care about the positive negative because I was gonna subtract them anyways. But yes, negative numbers can certainly be infinitesimal. What was I gonna say? Right. And as Michael was asking, or the next thing I was gonna say is, if you have an infinitesimal number and a bounded number, then the product will be infinitesimal and the sum is still going to be bounded. So this should be pretty obvious, I think. Right? If V2 is bounded, then here. Right? That's easy. And then similarly for the other one, if we have that, let's see. So anytime V1 is smaller than some number R, this product is going to be smaller than little r times big R, because V2 is smaller than big R. And then little r is arbitrary since V1 is infinitesimal. So little r times big R is arbitrary. And then V1, V2 is infinitesimal.
Is it also true that the standard part of V2 is the same as the standard part of V1 plus V2?
Yes,
Cool.
that was a good observation. If you have a, if both of these numbers are bounded, then the standard part is a, I guess, homomorphism. And then because V1 is infinitesimal, standard part is just 0. I mean, that could be another way to think about infinitesimals. Infinitesimals are just the numbers with a standard part of 0. And that's equivalent to the original definition, or what the original definition should have been, because Ethan pointed out that they are allowed to be negative. Now, I did write this property for a very specific reason. It does show up in the proof. So well, so if you take an n variable polynomial and with real coefficients, just standard real coefficients, and then you take any bounded non-standard numbers, then if we evaluate it, here. The standard part of the evaluation is the same as the evaluation of the standard parts. Now, rather than giving a formal proof of this, I'll just work it out in one example. But basically, the idea is, I guess this is a reflection of the continuity of polynomials. That's how I like to think about it. So, proof by example. And this is I don't know. I guess in my opinion, this fact is one of the most crucial facts used in the proof for at least one of the conditions. So and again, yeah, I'll just write some stuff because so if we, break up each non-standard number into its standard part and some infinitesimal, then this is just going to be, oh, yes, and I did assume bounded. So we have the sum of the standard parts squared And then we're adding to that to right. So I guess I did this. Oops. Is the expansion of that if you just FOIL it out, and then this is the expansion of this. So you just FOIL out each of these terms, and after you FOIL it out, you keep the standard parts, and then here you have bounded times infinitesimal, so it's infinitesimal. Bounded times infinitesimal is infinitesimal. Infinitesimals are bounded, so this is also bounded times infinitesimal, as is this, and the sum of infinitesimals is also infinitesimal. So all of this stuff is negligible, and this gives the result, at least in this specific example. And you could imagine, hopefully this example illuminates what you would do for a general polynomial. Yeah. Any questions or concerns here?
So you sort of, you hinted at this earlier. Is this just true for any continuous function that you can commute the standard part with the function?
I don't think so. I mean, it's not true for 1 over x, because the standard part of an infinitesimal is 0. So
yeah, I see.
Let me actually.
Well, but 1 over x is not continuous at
At 0.
0, so you want it to be continuous at the standard part of the number.
I still don't believe that this is the case, but
because the way I'm thinking about the standard part is it's kind of like an analog of the limit, and by definition, the limit commutes with continuous functions.
Just adding to my.
Wait. Let me answer this later. I forgot. I do have a slide about this, because even though continuity and differentiability is not used in the Ramsey theory paper, I figured I would still mention a few words about it just because we're on the topic. So let me come back to that in a few slides.
So Sohail, and another comment. Do you think a standard part is p limit?
The standard part is a p limit of what?
Of the thing. So a standard part of B is p limit
p
of
limit
B.
of the components. Yes.
Right.
Yes, that's correct.
So then you have continuity. Because you can take the p limit inside of the function and then you're fine, as long as your number is away from discontinuities, of course, meaning the sequence.
So yeah, you're right then. If you have a function f that's continuous at a real number, or I guess, why don't I just write what you just said? So actually, I think this is, well, yes, this is true. But again, let me just come back to this when we get to continuity and differentiability. I actually thought I'd be done sooner, but you guys are asking lots of questions, which is good. So it looks like it'll just take the full hour. I did hint at this earlier. The way that we extend the function is, well, first we denote it by putting a star behind the function. And then you just do the obvious thing. You apply the function to the tuple by just applying it to each of the elements, as we already did when we took inverses at the very beginning. And we do something very similar for sets. And we care about this because we're going to ultimately apply it to Ramsey theory, right? So if you have a set or a subset, then the hyper extension of that set is just going to be the set of all sequences where now the AIs are coming specifically from your set A instead of being any old natural number or any old real number. And we have the following fact that helps with the Ramsey theory. If you take any partition of the natural numbers, then the hyperextension of each of the sets in that partition gives you a partition of the hypernatural numbers. And again, proof of this is pretty easy. You just use the ultrafilter property.
Yeah, but it's specifically a finite partition, right? That's the important thing.
Yes, that is important. Finite partition. Good observation, Michael. I think I'll skip the proof of this one because here is, I guess, maybe the ultimate result that us Ramsey theorists would care about with regards to non-standard analysis. First, two elements, two non-standard numbers are really, they could be standard if you want, are indiscernible if for any set in the underlying space N, both of these numbers are in the hyperextension or neither of them are in the hyperextension. So basically, you cannot separate these two numbers into two different cells of a partition of the non-standard numbers if all you're doing is using these pleasant cells of a partition, these hyperextensions. Almost like measurable sets, right? Like if you pretend that these star A's are the measurable subsets of star N, which I really have no idea if this is a good analogy or not. This is just a personal thought. If you pretend that these are the measurable sets, then you can't distinguish these through measurable sets. You have to distinguish them through some weird non-measurable things. And the reason this definition helps is we have the following theorem. If you have an equation, which, we're just going to assume it's a polynomial equation because that's ultimately all we're going to apply it to. It probably applies to other types of equations, but just for safety and simplicity, if you have a polynomial equation and it doesn't have a trivial solution, which is a single element solution, because if you could plug in one number and get a solution, then any cell of a partition will contain that number. So it's partition regular for trivial reasons. If we ignore that, then the polynomial equation is partition regular over N, the original space that we actually care about and do our ordinary Ramsey theory on.
Wait, what do you mean for an equation to be partition regular?
Oh, maybe I shouldn't use n because I already here r. So for any finite partition of the natural numbers, one of the cells will contain x1 to xn that satisfy this equation. So just the definition of weakly partition regular.
Okay, cool, thank you.
Yep. So this polynomial equation is weakly partition regular if and only if there exist indiscernible non-standard numbers that are infinite, such that they satisfy this polynomial equation. And of course, we already said addition and multiplication happens component-wise. So, or we even already stated it for general function. So you just apply this function to each component, and the result should be 0. And this is, I guess in my opinion, the reason this is nice is that normally if you take different partitions of the natural numbers here, as your partition changes, your xi's will change, your solutions will change, right? So you first have to pick a partition, and then you have to search for a solution, and you can try to study things that way. But this is just a single universal solution, right? These numbers, once you have your polynomial, these numbers are fixed. You can just pick these numbers. And then the fact that they're indiscernible corresponds to partition regularity. Unfortunately, I don't know how to prove this, even though this might be.
It is not at all clear to me why this should be true.
Yeah, so this is maybe the most interesting theorem I stated. I can prove one direction. One direction is obvious. The other direction I can't prove.
Wait, what's the obvious direction?
If these numbers exist, then the original equation is partition regular. And it's obvious modulo being comfortable with non-standard numbers. Okay. So I guess it's proof of that direction. So we take what's given to us, and then now you take a partition of n. And now, because they're indiscernible, they all live in one set. All right, so this is where we use indiscernibility. If epsilon1 is, or sorry, xc1 is not in A1, then that means that xc2 is also not in A2. and xc3 and xc4 and so on are also not in A1 because they're all indiscernible. And here I maybe should have specified, I thought it was obvious, but since there's more than two of them, I mean they're pairwise indiscernible. And that's what it means for the whole collection to be indiscernible. So if the first one is not in A1, then none of them are in A1. And you do this for every set, and eventually you see that whichever one that the first one is in, they're all in there. Or I guess more directly, you could just use this and see that whichever AI0 star contains xc1, which exists by the previous comment that this is a partition, that AI0 is going to contain all the rest of them. But now, what does this mean? And you know, let me just do it this way. We can write out the components of each of these xcj's. And we know that n such that by definition of these things being in AI0 star means that most of the coordinates are in AI0. So there exists M such that EJM is in AI0 for all J by the ultrafilter property. I can intersect all of these, all J of these sets, and the intersection is non-empty. So take any element there. And now, right, P of oh no, sorry. Well, yeah, let me write this. I guess I should fix one detail, but hopefully the idea is obvious at this point. What I should have said here to make the finish more correct is which I already stated verbally, but this is we don't want one, we want this whole set. So this is we apply the function to each of the coordinates. Now, the number of coordinates that are equal to 0 is going to be in the ultrafilter, and therefore has non-empty intersection with this set. So therefore, for one of these coordinates, the polynomial evaluates to 0, and all of these e's are inside of a single cell of the partition. And that's the end of the first direction. So hopefully that made sense. Since we're just about over time, I guess I should maybe stop here and ask for questions. I think that was the main thing that I wanted. The rest of this, I mean, if you want to stick around, we can talk about continuity and differentiability, but I'm not going to use this on in the future. So this is just for your own personal amusement about non-standard real numbers. But I definitely wanted to discuss this theorem. So this is probably a good stopping point and a good point for questions.
Can we go back to the proof of the obvious direction of this theorem? Okay, so I think I understand up to like right below the horizontal rule line, or sorry, right above that. Yeah, so I think I understand why that's true. Yeah, because you're just intersecting a bunch of P large sets, right? So that's P large. Okay. And then you are looking at that thing, which is true by construction. And then you're looking at you are applying the P to each one of the X's, but only the first N components of the sequence.
No, this is just some notational, there's just a lot of notation here.
Yeah, okay.
So all of this is the first element of this sequence. So the first element.
I see.
Yeah, sequence. I have to take the first element of XC1, the first element of XC2, and the first element there, and then apply the polynomial.
Yes, cool.
So that's just the unfortunate side effect of sheer numbers of.
Oh, and that thing is, that number is inside of AI naught.
Yes, at least the number of indices for which all of these are in AI naught and this result is 0 is going to be in the ultrafilter, and therefore it's a non-empty number of indices.
And so the solution to P over the naturals is inside of AI naught. But what is that solution?
That's what we wanted, because we wanted to show that this polynomial is partition regular.
Yeah, I know, but what is the solution?
What do you mean? What is the solution?
Like you're supposed to come up with like x1, x2 to xn inside of AI naught.
Yeah.
But what are those xi to xn? It's not. Is it just?
Right. If you make this polynomial 0 and all of the elements are in AI 0, then I let this be my x1, this be my x2, and that be my xn.
Okay. Well, why the last one and not like the first one? Why not EI1, EI2, EIN? Or sorry, E1. Well, yeah, E1.
Because we're working with equivalence classes, when I write this, I don't know that every element is inside of AI 0. I know that P many indices are in A0. So I don't even know if this is an A0. It might be AI 0. It might not be.
Okay.
Similarly, if this is equal to 0, that tells me that P many of the coordinates are equal to 0. But I don't know if this coordinate is equal to 0.
But how do you know that the circled one is?
It's not necessarily this M. It's just that P many of the coordinates are 0. So I can intersect that set of coordinates with this set of coordinates because the ultrafilter is closed under intersection. And then that result will again be in the ultrafilter. So there exists at least one coordinate that makes both of these things happen.
Oh, okay.
So like if I was to write it out,
Still not. It's not really clicking for me. Yeah. Oh, okay. So you're just right. So you're just saying it exists. That's all you're saying. And the mth one is the one that exists.
right? To make both of these happen, you just intersect the sets for which each of them happen individually. But
Okay.
then this is in the ultrafilter by this assumption, and this is in the ultrafilter because we proved it up here. So the intersection is in the ultrafilter. So there are some indices for which this happens, and then you pick any indice, and then that's going to be your x's.
Okay. Cool. Yeah, I think that my like confidence is inversely proportional to the amount of subscripting and superscripting happening, and there's quite a bit here. Just
I can't blame you for that. I think similar approach.
Okay, thank you.
Not a problem. Thank you for all of your questions. Any other questions about anything that was said so far? I might have to, I guess one thing I didn't mention is base P expansions for hyper natural numbers, but I can squeeze that in either next week or on week 3 or something. But yeah. Well, looks like there's no immediate questions, so I'll just end the recording and let you guys either think about questions or leave.
Okay, thank you.